is the maximum or minimum, right? You talk about the maximum or minimum. So there's a quadratic right there, that green one on the left, and it has a maximum value of, and it's funny, some people really have a hard time with this in grade 10 because they think to themselves, well, the maximum value is negative because it goes forever down. So that's like your maximum, but that's not what we mean, right? What we mean is this function has a maximum value. It looks like it's about 6. Hard to tell with the scale without the green lines. A maximum value that it will never go above, right? This graph quadratic has a maximum value that it will never go above. That's what we mean, and everybody understands that now. But you're introduced to that concept in grade 10. And then in grade 11, you see more functions, and again, some of them have maximum or minimum values. Maximum and or minimum values, right? A circle would have both. But the graph on the right there, the red one, which is a cubic function, y equals x cubed, that's a transformed version of it, it has neither a maximum nor a minimum. It goes forever down and forever up, right? So this is just one of the characteristics that we know we can help to describe graphs. Those are all absolute or global maximums, minimums. Sometimes we refer to them as extrema or extreme values. Okay, so those are global or absolute extrema. And maxima or minima is actually the plural version of maximum and minimum. Okay, so there's another thing called local maximum or local minimum. So even though the cubic graph on the right there doesn't have an absolute maximum, between the values of 0 and positive 5, it does have a local maximum. Between any interval, a graph will have a local maximum. Even if I chose this interval here, you see that okay? There's a local maximum. It occurs right there at the end of one of the intervals, right? So that would happen if I pick an interval that doesn't have a change in direction in it. So that's got a local, every interval will have a local maximum, and then a local minimum would happen there. That's not very interesting, though. It does happen, and it is something that you might talk about. I mean, but it's pretty obvious. But in some ways, what we're talking about today, what we're more interested in, is when I have an interval that has that kind of change in direction. So that certainly that's the absolute maximum of that function, but we would also call it a local maximum within that interval. Okay? And so then a cubic would have a local maximum within that interval and a local minimum, that's interesting, within that interval. Okay? Does that make sense? So what do we know? So blah, 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 there's that blurb on that. These are often turning points in the relation, right? So a turning point is where it changes direction. So this stuff that we've been talking about with rates of change, and in particular, instantaneous rates of change, slopes of tangents, how would that help me determine something to be a local maximum or a local minimum? So this down here at a local maximum, the instantaneous rate of change or the slope of the tangent would be what? Zero. Good. Right? Let's go back up and take a look. So at that point, my slope of my tangent will be 0. What is the slope just before I hit that turning point, that local maximum? What would the slope be like there? Well, just before, that's a positive slope. Yes? Just after, what would that be? A negative slope. So if I have a point on a curve where the slope of the tangent, the instantaneous rate of change, is 0, it is either a local maximum or a local minimum, right? A local minimum would have a slope of 0 as well. Okay? So if the slope of the tangent is 0, it's a local maximum or a local minimum, or it could be an absolute maximum or minimum as well. And then if the slope just before that point, right, to the left, like we always think about left to right. So when I say just before, I mean just to the left. If it's positive and then the slope after is negative, then it's going to be a local maximum. And then alternatively, if the slope right before is negative and then the slope right after is positive and the slope is 0 at the point, then it's a local minimum. Does that make sense? Can you visualize that? Okay, so let's add that. At a local maximum, the instantaneous rate of change will be 0. Do you remember when we said it's neither increasing nor decreasing, like at the vertex of a parabola? Remember we talked about that in the last unit. So if it's decreasing, and then you hit the vertex, it doesn't include that point. And then after the vertex, it's increasing. You know how we talked about that? Well, here's the mathematics showing that it's neither increasing nor decreasing. The slope is 0. That's no rate of change. Whereas before, it's decreasing, and after it's increasing, you can see that by the slopes. Okay, anyway, at a local maximum, the instantaneous rate of change will be 0. The rate of change before the point will be, what is this? A local maximum will be positive. And after the point will be negative. So 0, before it will be positive, and after will be negative. At a local minimum, the instantaneous rate of change will also be 0. The rate of change before the point. Sketches like this are so helpful. It just allows you to visualize it, right? So the rate of change before the point will be negative. And after the point will be positive. Any questions about that? Okay, so let's put this into action and try this. Show that each of the following is a local extrema of the function f at x equals x cubed minus 9x squared plus 24x minus 20. That's a big one. And determine if it is a local maximum or a local minimum. So to show that it is a local maximum or local minimum, we have to find the slope of the tangent and show that it's 0, right? That's what we just looked at. That's what we're going to do. Slope of the tangent is, remember this, the limit as h approaches 0, f at a plus h minus f at a over h. Where a is 2 and f at a, or f at 2, is 0, gives us that.
So x cubed, but x is 2 plus h cubed, minus 9 times 2 plus h, plus 24 times 2 plus h, minus 20 minus 0, all over h.
You can cube the binomial the long way, or you can try to follow what I'm saying. The first term cubed, so 2 cubed is 8. The second term is your Pascal's triangle coefficient of that row, which is 1, 3, 3, 1. So the second coefficient is 3. So 3 times the first term squared times the second term. So 3 times 2 squared, 4. So that's 12h plus coefficient 3 times 2 times h squared. So the second term squared. And then the coefficient was just 1 times the second term cubed. If you didn't follow that, that's okay. You can do it the long way, or you can go back and watch this after, watch that video that I posted about cubing binomials. Or you can ask me about it, and I'll slow it down and do it for you again after. Oops, I missed a squared there. Okay, minus 9 times 2 plus h squared. See, this one you should be able to do, right? It's the first term squared plus 2 times the first term times the second term, plus 4h plus the second term squared, plus 24 times 2 plus h, so 48 plus 24h minus 20. Equals the limit as h approaches 0. If you want to collect like terms at this point, you can. So we can put it in order. So h cubed, I've got 1 squared term. I've got 12h and 24h. So that's plus 36h. And then 48 minus 20 is 28, plus 8 is 36. And then I'm expanding this last little bracket here. So minus 36 minus 36h, that worked out nicely, minus 9h squared, and I think I got everything there. 36 minus 36, 36h minus 36h. So I've got h cubed, 6h squared minus 9h squared minus 3h squared over h. How does that feel? It's all right. Okay, so let's simplify. Limit h approaches 0, common factor. Of h squared minus 3h. So if I sub 0 in, I'll do it this time, which equals 0 squared minus 3 times 0. So that's 0. There you go. Slope of the tangent is 0. That's what we were expecting to find. I think that means we did it right. Like we were told in the question that it was a maximum or minimum, right? It said show that it is, not determine if it's a local maximum or minimum. Show that it is. So we were expecting to get 0. So that's good. What else are we supposed? Everybody good? What else are we supposed to do? Determine if it's a local maximum or a local minimum. So here's what we're going to do. In this case, I'm going to let h equal some very small negative number. Negative 0.1 I'm going to use. And I'm going to sub that in to my slope formula. So instead of letting h be 0, do you remember? Let's see.
that right? I don't think it is. Ah, wrong one. Demo. So this was our demonstration yesterday, how as h gets smaller, remember what's happening, the points that I'm finding the slope between, the average rate of change between. If h is anything other than 0, I have 2 points and I'm finding the rate of change between them because I used the rate of change formula. Right? The rate of change formula. So, if h is anything other than 0, I'm finding the rate of change between 2 points. But when h becomes 0, all of a sudden it's 1 point, and it's an instantaneous rate of change. So that's where we get that limit as h approaches 0. Okay? But if I make h just something really, really small but negative, then I'm actually subtracting from a, and I'm finding what the slope is right before the point on the graph. So if I made it the vertex, and there you go, it's 0, right on. But right before, if I make h really, really, really small, I'm finding the slope before. And if I make h really small but positive, I'm finding the slope after. Because h is what I'm adding to the a value, right? It's not a point. H isn't a point. H isn't like 1, the point 1. H is what I'm adding to the x value. It's the difference between the two. So if I make it small negative on before, small positive after, you don't want it to be too big because it's possible that you could have functions that have like 2 turning points really close to each other. And if you made h like 1, then you might actually have turned again or something, right? So as a rule, we're going to keep it really nice and small. So then I'm going to find the slope. Whoops, I don't want that. I'm going to find the slope of the tangent when h is negative 0.1. So I just sub it in. So it's negative 0.1 squared minus 3 times negative 0.1. Do that on my calculator. This is going to be positive. This is going to be positive because it's 2 negatives. But I'm adding 2 positives, so I actually kind of know just by looking at that part that it's going to be positive, but it ends up being 0.31. And then I'm going to let h equal positive 0.1 and find the slope of the tangent. 0.1 squared minus 3 times positive 0.1. So 0.1 squared is going to be very small. And 3 times 0.1 is going to be not quite as small, so I'm subtracting something bigger. So that's going to be negative for sure. So it works out to, I believe, negative 0.29. Yep. Absolutely. Sometimes it's easy. Sometimes I'll talk about that in a minute. Okay, so here's what I'm going to do. The slope before was positive. The slope after was negative. What does that mean? Therefore, local maximum. Instead of memorizing, so if the one before is positive, the one after that, instead of memorizing, I just kind of think about it every time, right? I just understand it, draw myself a little diagram or visualize it in my head if I can, and then if sometimes my answer works out, so if I'm doing all the work and I get my slope of the tangent is the limit as h approaches 0 of h.
I don't have to sub in to show what's happening here. If the limit as h approaches 0 of h, if I put a negative value in, it's negative. If I put a positive value in, it's positive. Or if I got negative h here, same thing. I don't have to actually like let h equal something. I can just, but I would still say something.
I would say this. I would say if h greater than 0, slope of the tangent is positive. And if h less than 0, slope of the tangent is negative. I would still say that, but it's a statement, not a test, because we don't have to sub into h. Show it. Does that make sense? You still could. You could do it the other way if you wanted. You could just sub in if you want. But you wouldn't have to. We're not, so Sam, you asked a question, and I'm going to give you a bit of a better answer than I did last time. We're not going to look at this case, but there is a case with a graph that goes like this. It's called a twist. And so it's got a positive slope before, it's got a negative, or it's got a slope of 0, and then it's got a positive slope after. So there are other cases where you would have a slope of 0, but it's not a local maximum or minimum. So you absolutely have to check on both sides in case you have some kind of a twist or something. But we're not gonna, that's not gonna pop up for us right now, but it will later. Okay, let's try another one. So that's the same, whoop, where'd it go? That's the same function as before. But this time when x equals 4, last time notice it gave you the whole point. What was it, 2, 0 or something like that? This time it only gives us the x value, so we have to find the y value. So one extra step, you just got to sub in first to find the y value. A mistake that, what's going on with this thing? A mistake that some people make is they just subtract 0, like we did in the first case. They just always subtract 0. If you change the x value, this is like the y value, right? If I change the x value, I'm changing the y value, so I don't always subtract 0. So you got to find it first. So make sure, don't copy what we did in the first step and just subtract 0. Find the y value, and then do the same process. So I'm going to let you try this one on your own. I'm just going to come around and see how everybody's doing. Okay, so I'll put, I don't know how many people are done, but I'll put a little bit of this up. There's my first line, just my intro, and then subbing in 4 plus h cubed, 4 plus h squared, 4 plus h, and so on, and my negative 4 value, subtracting negative 4. And then expanding, so you can check your work if you want.
So after you've kind of simplified everything and a lot of things cancel out, I got h cubed plus 3h squared. Divide the h's, h squared plus 3h, which is a slope of 0. Perfect. And so now I want to let h be something small and negative. Slope of the tangent is negative 0.1 squared plus 3 times negative 0.1. So that's going to give me negative 2.9. Is that right? Whoops. I mean negative 0.29. And then let h 0.1. So beforehand is negative, afterwards is positive. Local minimum. Everybody good with that? Okay, so just quickly, let's take a look at a graph of this. X to the 3 minus 9x squared plus 24x minus 20. Local maximum when x is 2, and you see that the point is 2, 0. Local minimum when x is 4, and it's 4, negative 4. So it does match. Always good to visualize, right? Don't get caught doing just the algebra without thinking about what it is we're talking about. We're talking about a function here. This is the cubic function. All right. Page 112, number 5 and 6. Anything that has a sine or a cos in it, don't do. So there's like, I think it's like C and D in 5 you don't do, and D in 6 or something like that. If it's got a sine or cos, don't do it. Do the rest of them. Good?